Okay, this video will go through some different uh, things that can happen with Le Chatelier's principle. And so basically what you got to be able to figure out is when something is done to a reaction, will the reaction shift to the left or the right? And so that's kind of what we're trying to figure out is which way it will shift. All right, so anyway, when you're thinking about the shift, I mean, it can always be worked out with a Q versus K type of thing. So remember that if you have the equilibrium expression, so like K or Q, all right, and for this one, it would be equal to SO2 to the second power times O2 to the first over SO3 to the second power. Okay, so now when you and so this could be Q or K if it is at equilibrium, or if it's not, we would refer to it as Q, but you'd write the expression the same. All right, and so if Q does not equal K, the reaction is going to shift one way or another so that they're equal. And so anyway, now you don't always have to write this out, but you just got to be able to think about it. So anyway, basically, if we add SO3, so we're adding stuff to the left side of the equation, all right, well, the reaction is going to shift to the right to get it back to equilibrium. Because if we add more SO3, it has to reduce that, and so it's going to go to the right. Okay? One thing that you can kind of think about when doing this is it's kind of hard to make this work out, but I like to think about it like a water tank connected to another water tank, and then there's like the water's right up to the top. Okay, in a way, I mean, this doesn't always work, but if you add more on this side, it's going to run over to this side. And if you add more onto this side, it's going to run this way. I know that's not a perfect analogy, but that's kind of the way I think about it. All right, so if you remove some O2, so if you take some O2 away, it's going to shift to the right. If you were to add O2, it's going to have to reduce that O2, and so it's going to shift to the left. Okay, that's all we're doing is saying right or left. All right, now here's another example. All right, and it has to do with pressure. Now, pressure is a little more complicated, and so what you got to do is draw a picture or look at it. And so basically, on the left side of the equation, all right, so here's my container. On the left side, I'm going to count the moles, and I like to draw this picture. I've got 2 moles of SO3 here. And on the right side, I have, now remember they're all in the same container, but I like to just divide it up like this. On the right side, I have 2 SO2s, so there's 2 there, and 1 O2. Okay, and so 1 O2. All right. Now, anyway, if you increase the pressure, this reaction is going to want to decrease it to keep it at equilibrium. Now, here's the thing. If the temperature is not changing, so we're not saying the temperature is changing, this side of the container has 2 moles of gases striking the edge of the container and causing pressure, whereas this side of the reaction would have 3 moles of particles striking the edge of the container, causing a pressure. So if you increase the pressure, this thing is going to want to decrease it. So what would decrease it? Having 2 moles striking or 3 moles? Well, 2 moles striking the container would be less pressure than 3, so this one's going to shift to the left. Okay, now if you decrease the pressure, so this is like somebody manipulating. Let's say somebody decreases the pressure. This thing is going to want to increase it, and so it's going to shift to the right because there's more moles striking the edge of the container. Okay, now adding neon gas. So let's say that we put neon gas in the container. Okay, well, here's the thing about adding a neon gas. The neon gas is not going to affect the partial pressure of the gases in this equilibrium expression. So whenever you add an inert gas, which is normally like as a gas that's not going to react and use up any of these or make more of any of these. Okay, so adding an inert gas has no effect, so no change, no shift, no change or no shift. All right, that's sometimes they like to throw that in there like adding a noble gas or something. That's not going to cause a shift in equilibrium because it doesn't affect the partial pressure of any of the gases in our problem. Okay, now here's another one that they like to do with this volume thing. So I'm going to draw the containers again. It's the same reaction here. And so anyway, on this side we have two SO3s, okay, striking the side of the container, 2 moles, and on this side we have 3. So now you got to remember Boyle's law, which it says increasing the volume of the container. Well, basically, here's the thing. If the volume goes up, the pressure goes down. Okay, they have an inverse relationship. If the volume goes up, the pressure goes down. That was a gas law unit where we could graph pressure versus volume or volume versus pressure, whatever. Okay, but if one goes up, the other one goes down. So if we increase the volume of the container, the pressure is going to go down. The pressure goes down. So this reaction is going to shift to make the pressure go back up. So if we increase the volume, the pressure is going to go down. So the reaction is going to shift to the right because there are more moles. So it's going to shift to the right. Okay, now if we decrease the volume of the container, okay, decreasing the volume of the container is going to make the pressure go up. And if the pressure goes up, this reaction is going to shift to make it go back down. So it's going to shift to the left because there are fewer moles of gas. It's going to shift left because there's fewer moles. Okay, now here is temperature. So here's what I like to do with temperature. The easy way to do Le Chatelier's with temperature is just take your delta H, so they'd have to give you the delta H, and see if it's exothermic or endothermic. And you see if that number is a positive number. So I just like to write it. Remember, if it's positive, it goes on the left side of the equation. So I just like to write my kilojoules over here. That helps me. Okay, so it's on the left side. Now, if it was exothermic, I'd write it on the right side. Now, increasing the temperature, I know temperature is not like a physical thing, but you can think of it like increasing the temperature would be like adding more kilojoules to this side. Okay, so like if you add more kilojoules, this reaction is going to want to lower the kilojoules, so it's going to shift to the right. All right, so if you increase the temperature, it's like adding kilojoules to the side. Decreasing the temperature, that would be like taking kilojoules away. If you take kilojoules away, it's going to shift to the left. Okay, so with temperature, just write it on the side of the equation that it goes on and think about what would happen when that, just treat it like a physical thing. Okay, now here's another type of thing that can happen with Le Chatelier's. So, number one, adding more silver nitrate. Well, if you remember, when we write the equilibrium expression, so we would write this one would be K is A plus 1 and nitrate NO3 negative 1. Okay, we would leave out, solids are left out of the equilibrium expression. So whenever you add a solid or a pure liquid, nothing happens. Okay, so adding more AgNO3, no shift will happen. Okay, adding more Ag. Okay, well, K wants to equal Q, So basically, if we add more of it, we have to take some of it away, so it's going to shift to the left. Okay, removing some AgNO3. Well, once again, AgNO3 is not part of the equilibrium expression, so there would be no shift. Okay, removing some NO3, -1. All right, so if you remove some NO3, this reaction is going to want to replace it, so it's going to shift to the right. Okay, last one. Now, here's something that happens, and this sometimes takes a lot of knowledge about how this works. But anyway, you can see that, okay, now they're going to add some HCl to this thing. So basically, here's what we have. All right, so we have this beaker, and in the beaker, there's some silver nitrate that didn't dissolve, and it's at the bottom, okay? So it's like at the bottom. But in here, we have some nitrate, and we have some silver floating around in here in this solution. All right, that's dissolved. Now, if we add some HCl, so what's going to happen is if we add some HCl, well, what will happen is the Ag and the Cl will go together, and what will happen is the Ag and the Cl negative, -1, they're both AQ, they'll go together, and they're going to make silver chloride solid. And so what will happen is these two will go together, and also they're going to form an insoluble thing. And so then there's going to be some AgCl on the bottom too that doesn't dissolve. And so in essence, basically what it's doing is it's removing some silver ions from the solution. So the HCl is going to remove some silver, so it's going to shift to the right. Now, to know that, you would have to know a lot of solubility rules, and on the AP test, they would probably tell you something about maybe the silver chloride is an insoluble and it would form a precipitate or something like that. Okay, adding some KNO3. All right, so it would be a little bit different than the one up above, but basically we have this again. So we have the AgNO3 on the bottom, that's a solid, and then floating around in the beaker we have some Ag and we have some nitrate ions floating around. Now if you add KNO3, well, the K and the nitrate, remember nitrates are always AQ, that's one thing that the AP test wants you to remember. And the K is not going to react with the silver, okay? But then you're just basically adding more nitrate. And so adding more nitrate is going to make it shift to the left to remove some of the nitrate. It's kind of like the common ion effect there. All right? Okay, now adding some NaOH. All right, so here we go. We have the silver nitrate at the bottom. So silver nitrate, it's a solid, and then we have the Ag and we have the nitrate in here. Now, when you add the Na, okay, so we can add the Na. Well, remember all nitrates are aqueous, so if the Na went with the NO3, that it's not going to form a solid, okay? But the OH -1, it's going to go with the silver, and it's going to form a solid. And so these two will go together, and silver hydroxide is a solid, so it would sink to the bottom. And so in essence, you would be removing some of the silver, and so it's going to shift to the right. Okay, that's it for this video.